Hello, everyone, and welcome back. If you think about what we've been doing over the past few video lectures, we've been sort of going over these techniques or these ideas, these concepts that we learned in maybe grade school, things like area and volume. And we're showing how we can use calculus to calculate these things for very, very abstract shapes. In particular, we can create these shapes using a solid of revolution and then find the volume using maybe the washer method, the disk method, or even the cylindrical shells. We have this notion of area coming from these definite integrals, which is abstractly the area under the curve, or it's really the area from the curve to the x-axis. So we're going to continue today by talking about these abstract notions of things that we already commonly understand. And we're going to go all the way back to the beginning. We're going to talk about length. So this is the sort of one-dimensional equivalent of area, if you think of that as being two-dimensional, and volume, you think of that being a three-dimensional technique. And we're going to do the same thing, right? If you're a betting person, you should be able to bet with very, very high odds that we are going to use a definite integral to calculate lengths of curves. So let me show you what I mean. Let's start with the complete basics here. And imagine that I give you just a very, very simple line segment. So imagine I give you just this line, and I ask you, what is the length of this line? Well, you could potentially just get out your ruler and you could measure it, but we're going to think about this absent of any units. So the question is, how do we find the length of this thing? Well, we can reach back into the recesses of our mind and think about what the Pythagorean theorem tells us. And it really tells us that that length is the square of that length that we're interested in is equal to the square of this length plus the square of this length right here. Now, if we put these things in terms of maybe a coordinate axis here, so you imagine I have horizontal and vertical components, say x and y, then the base of this thing becomes, say, delta x. So that's maybe the change in x, so the change over the x coordinates. And the height of this thing becomes delta y. So that maybe if we call this point, say, AB, we call this point CD, then delta x is C minus A, and delta y is equal to D minus B, right? So the change in the x and the y coordinates. But that tells me that the length, very simply, is equal to the square root of delta x squared plus delta y squared, right? So I'm probably telling you something that you already know. I don't think you should be that impressed by this. But let me offer up a different question. Okay, so imagine I give you a curve. So I'm going to represent this curve in terms of a function y equal to f of x. We'll just draw a sort of random curve to get the point across here. Imagine I give you, something that looks like this. We call this thing y is equal to f of x, and it's going to go between points x equal to a and x equal to b, as usual, right? Our usual endpoints that we always have. So this point is going to be a comma f of a. And this point is going to be b comma f of b. So just the ordered pair, x is equal to a or b, and then you put that into f, that gives you the y value. Okay, imagine I give you the following problem. I say, okay, smarty pants, you could do the first one easily. Why don't you tell me what the length of that curve is, right? So you can imagine this as, maybe somebody traversing some sort of windy country road. You want to know the distance that you traveled. So what is the distance that you traveled? It's got to be, or at least just from a visual inspection, it's bigger than just going from the beginning point to the end point, because there's these long sort of arcs in the middle. So what do we do? Well, let me show you. So if this is where we started, maybe I need to pull this out just a little bit. So this is going to not look great, but oh, it actually doesn't look bad. Where we ended is right here. What we're going to do is we're going to approximate that length using straight lines. So the same type of idea that we used for areas, where we approximate areas using rectangles, things I can find the area of very, very easily. I'm going to do the same thing for this length, and I'm going to approximate this curve here by something that is just a bunch of piecewise straight lines. So imagine I put in some point, say x1 here, and I go up to that point on the curve, and I sort of disregard any of the bendiness of this curve, and I just draw a straight line between those two things. And then what I can do, much like what I do with the integral, I do the same thing for another point. Let's imagine that point x2. So maybe I should label these. This is x1, f of x1, x2, f of x2. And you know what's coming, right? You can smell it. This feels like a Riemann sum all over again. So let me draw a couple more of these in here just so we can get the point across. I'm drawing them purposely far apart, of course, just so that we can really see what's happening here. And then maybe let's put an xn on the back here. So I get xn, f of xn, and let me put a drawing in here. Okay, so you imagine that I sort of partition all of these things out, and just like I always do, I'm going to assume that the distance between xk and xk plus 1, or k minus 1, doesn't really matter. We want to keep it positive. This thing is fixed for every single k, right? So we have this delta x movement here. Okay, so then what is just the length of each one of these line segments, right? So the length of a line segment, length of segment between xk minus 1 and xk, we're going to call this thing lk. So L for length, k because it's between k and k minus 1, or k minus 1 and k. Well, the Pythagorean theorem tells us, just like from above, this thing is going to be the square root of delta x squared plus, now our delta y is going to be the change in y values. This will be f of xk minus f of xk minus 1. And then that whole thing is put up underneath this square root. And so this tells us that the length of the curve, which I will denote by, say, capital L, well, this thing, just like with the Riemann sum, this is approximately given by the sum over all of these little line segments here. And the question is, what happens as we let delta x go to 0? Because this is now starting to look like, starting to feel like a Riemann sum. But we don't have that delta x on the back end, right? So it's not quite there. There's still a little bit more work we need to do. So what we're going to do is we're going to simplify this f of xk minus f of xk minus 1. And we're going to do that using the mean value theorem, right? So one of the most important theorems in all of calculus, maybe second only to the fundamental theorem of calculus itself. Let's see. The mean value theorem tells us that f of xk minus f of xk minus 1, this is equal to, so you might have to look back up the mean value theorem for this, but this is equal to the derivative of f at some point ck multiplied by the change in x. Right? And so this is really just the derivative at some ck times delta x, where ck is between xk minus 1 and xk. And again, let's just put a little note here for ourselves. This is the mean value theorem. Mean value theorem. Now, try not to get confused with this, right? This is the differential mean value theorem. We introduced the integral mean value theorem, but they're both intimately related by the fundamental theorem of calculus. But let's see what this does to us, right? What do our L sub k's now become? So let me skip to another page here, and we'll simplify this out. We have said that LK is equal to the square root of delta x squared plus the change in y squared. So let me put that square root over the whole thing. Now, from the mean value theorem, I get that this is equal to delta x squared plus f prime of ck squared, times delta x squared. So I broke up the product because, as you can see, I'm going to factor out a delta x squared from both of these terms. And so this leaves me with 1 plus f prime of ck squared, and then all times delta x. So I pull out the delta x squared, it comes down to the square root, the square and the square root cancel each other, leaving me with just a delta x. But now we can see it, right? Because now the length of the curve is given by the limit as n goes to infinity of this discrete summation over the LKs, which, if we put in what we now know about the LKs, this becomes the discrete summation of the square root of 1 plus f prime of ck squared times delta x. Now, this is just a Riemann sum. This is a Riemann sum of the function square root of 1 plus f of x, f prime of x squared, sorry. So this tells us that in the limit, I get the integral. Now, remember, we're going from a to b. Those are our endpoints always. 1 plus f prime of x squared, all under the square root, and then that differential, that infinitesimal of d of x. So this is the formula for the arc length of this curve, the length of the curve. So we call this the arc length because this is related to an arc, a curve. Let me give it to you properly. Let me give it to you in a concisely written statement. And what I want you to notice about this is I'm assuming not only continuity of the function, but I have to have smoothness of the function. So that means that the derivative is continuous as well. Why is it that I need smoothness of the function? Well, look at the formula. The formula involves the derivative, not just the original function. So let's call this a definition. So if f prime is continuous on the set AB, or on the interval AB, then we'll put this in red because this is the definition, then the length As I said, we also refer to this as arc length. We'll sort of use these things interchangeably here. Of the curve y equal to f of x from the point a comma f of a to the point b comma f of b. So just like my picture on the previous page here, is the value of the definite integral so L is equal to A to B. So basically exactly what I have above, right? We're just sort of summarizing information so that it's quickly accessible in case we don't want to have to rederive this every time. And, just for the sake of simplifying this a little bit, or just so that we know if we're given a curve in terms of y, we can also write this as, using Leibniz notation. Okay, that's not too exciting, right? Or it's kind of exciting. We found another way of using Riemann sums to evaluate a question of, say, practical interest. But the not exciting thing maybe about this is that it's, again, just a definite integral, right? We just need to know how to set it up. And now we've got a formula. Of course, once we have a formula, that means that we can start doing examples and we can start seeing how this thing works actually in practice. So let's take our first example here. Find the length of the curve which is going to be given by y equal to 4 times the square root of 2 over 3 x to the 3 over 2 minus 1, and x is going to run from 0 to 1. Okay, so there's some kind of ugly numbers out front, but that's okay with us. Let's start tabulating off the pieces that we know. We actually don't even really need to sketch this, right? Because now we just have a sort of formula that we need to plug in the appropriate pieces to. So let's say A is the left endpoint, that's equal to 0. B is the right endpoint, that's equal to 1. And now, so maybe I'll just put that in a little box to save for later. Let me, of course, now I need my derivative. So this tells me that dy by dx, just using Leibniz notation again, this is 4 times the square root of 2 divided by 3, multiplied by 3 over 2, x to the 1/2. And we can simplify this thing a little bit. This is going to give me 2 times the square root of 2, x to the 1/2. So then we're going to be asked to square this thing, right? Go back and look at the formula right above. This tells me that my derivative with respect to x squared is going to be, now 2 root 2, square that, going to give us a nice 8, and x. So you probably looked at this curve and you thought, those are some really ugly numbers down front, Jason. Why would you do that? Now you can see why, right? Things sort of simplify very, very nicely for us. So let me flip over a page here, and we'll actually compute the length of the curve. So the formula tells us that the length here is now given by the integral from a to b, 0 to 1, of the square root of 1 plus, now the derivative squared, we might as well write it just so that we've got it somewhere for us. The integral from 0 to 1 of 1 plus 8x square root. You're going to have to use substitution if you want to do this integral. You're going to substitute for 1 plus 8x. I refer you back to the previous video on substitution for definite or indefinite integrals. But in this case, the antiderivative is not really that difficult to find. So we're we're going to go ahead and just compute it. So it's 2/3 times 1/8. The 1/8 is coming from the substitution for 1 plus 8x, and then 1 plus 8x to the 3/2. And this is running from 0 to 1. Now, calculate a problem. Nothing exciting, right? So this is going to give me 13/6. And just in case you're curious, this is approximately like 2.17. But at this point, the exact numbers don't really matter. It's about how we got there and that we applied the formula correctly. Okay, let's keep going, right? The best way to learn mathematics is just doing examples. You have to get your hands dirty with these things. So let me give you another one. So find the length of the graph of, let's say, f of x is equal to x cubed over 12 plus 1/x. And in this case, x is going to run from 1 to 4. Okay, so again, don't really need a picture here. We just need to be able to apply the formula appropriately. So we can clearly see, again, if I denote this in red, the endpoints are given to us, nothing too mind-numbing. And that means that the only ingredient that we're missing here is a derivative. So the derivative of f is given by x squared over 4 minus 1/x squared. And so this tells me that I'm actually going to need 1 plus the derivative squared. I might as well simplify this whole thing out, and you'll see why as I sort of progress through this. But this gives 1 plus, so let's just write down what we have, just so that everything is all in one place. So now I get 1 plus, and so here we get x to the 4 over 16 minus 1/2. The square on the x squared on the top is going to cancel with the x squared on the bottom. And then we just double up. So 2/4, that's 1/2. And now plus 1/x to the 4. Now I've got a 1 out front, and I've got a minus 1/2 in the middle. This leaves me with x to the 4 over 16 plus 1/2 plus 1/x to the 4. And very, very clever maneuver here, but you can actually see that this thing is a perfect square. So this thing becomes actually x squared over 4 plus 1/x squared, all squared. So that's why I did the 1 plus the derivative squared, right? Because the whole thing simplifies into a perfect square. And why do I care that it's a perfect square? Well, I'm taking the square root of this thing. So, life just got a whole lot simpler for all of us. So therefore, the length of the curve L is now given by the integral from 1 to 4 of, in our case, this is 1 plus the derivative squared. Let me just skip that step, and let's actually write it out. X squared over 4 plus 1/x squared squared, all under the square root. This leaves me with an integral from 1 to 4 of x squared over 4 plus 1/x squared. Now we've got a relatively easy integral to simplify, because these are just, the terms are just x to some power, right? So we're just going to increase the power by 1 and divide by that new power. So I get x cubed over 12 minus 1/x to the 4. And this is all running from 1 to 4. And again, a little bit of a calculator problem here. So once you plug in those bounds, you get a nice 72/12, which is really just 6. Okay, so again, the final answer, the number, it's not as thrilling to arrive at. The real thrill of the problem here is using the formula correctly and putting in all the pieces that you require. And so certainly when it comes to computational effort, these arc length problems are considerably simpler than the volume problems that we've been considering prior to this, right? It's a relatively straightforward process because it's just applying this this relatively simple formula. Okay, let me give you one more. So example number 3 for today. Let's say find the length of the curve y is equal to 1/2 e to the x plus e to the minus x. And this thing is going to be from 0 to 2. Okay, so again, endpoints are already given to us. Nothing really too mentally heavy there. So we'll keep that off to the side for later. Okay, and that means that really all that's left is finding some derivatives, right? It's the same process over and over. So dy by dx, the Leibniz notation here, this is just 1/2 e to the x, because e to the x differentiates into itself, minus e to the minus x, right? So this is a chain rule application. The minus comes out of this and is multiplied in front. And then, again, I'm going to need this thing squared. We might as well do the simplification before we put it into the integral. This is going to leave me with, so I'm going to do the expansion right away. This is e to the 2x. That's the same as e to the x, and then all squared. Minus 2, that's e to the x times e to the minus x. Those things are reciprocals of each other. And then plus e to the minus 2x. And so that means that if I add 1 to this thing, so maybe we should put some implies here just so that we can follow our line of logic. If I add 1 to this thing, you notice that there's a factor of 1/4 out front here. So I want to put the 1/4 in front of everything. 1 is the same as 4 over 4. So that is essentially, in the middle term, is going to be minus 2 plus 4. So I get 1/4 e to the 2x plus 2. That's the minus 2 plus 4. Plus e to the minus 2x, which, again, perfect square. So this gives me actually 1/2 e to the x plus e to the minus x squared. And I love perfect squares here, right? Because perfect squares are going to simplify that arc length computation for me because of that pesky square root that shows up all the time. So L is given by the integral from 0 to 2, a is equal to 0, b is equal to 2, and then the square root of 1/2 e to the x plus e to the minus x, all squared. Sorry, I had to sort of squeeze that in a little bit. But this leaves me with the integral from 0 to 2 of 1/2 e to the x plus e to the minus x. And so in this case, antiderivatives are, again, relatively simple. You might, if you're not quite comfortable with substitution yet, you should use the substitution method to find the antiderivative of e to the minus x. This is a nice little round of practice for everyone. But I will give you an answer. You can think of this as a solution key if you want. So running from 0 to 2, in this case, you get 1/2 of e squared minus e to the minus 2. Again, these are terrible, horrible numbers, right? E is an irrational number. This is going to be some decimal place decimal that is really, truly terrible. But it's like 3.63 if you want to put that into your calculator. Again, final number doesn't matter. I really like just leaving things exact. So I think my second to last line would be sufficient here. because that is actually the exact answer to every possible decimal place, right? I'm not doing any rounding by making this thing just a little number. Okay, so that concludes our introduction to arc-length. In the videos that follow, we're going to just discuss some small technicalities related to this. But for the most part, we've got the general method now. And so we can start calculating the lengths of curves.